Good morning, everybody. Good. So what I'm talking about at the moment is really a classic analysis of critical phenomena. It's the Ising model, and the Ising model is not because it's the most general model, it's the classic model. One explains all these kind of phenomena that are used in many different fields of physics. They are used in critical phenomena, from Ising models, magnets, to liquid crystals, polymers, up to quantum phenomena, and field theory in high energy physics. So that's why I do it. And today I would like to generalize what we did from the Ising model to the n-component model. So instead of having one single component, like for the uniaxial ferromagnet, we now have many, say n, and you could have different classes. If n is 1, of course, we are back to the Ising model. If n is 2, then that's called the XY model, where you have spins that are planar, and that's a very particular and special case. If n equals to 3, that's called the Heisenberg model, and you can also have higher order models, and they have their particular meaning in different contexts. So in general, what we have is still a Ginzburg-Landau free energy functional. It has the standard terms, it has a mass term, it has a phi to the 4th term, and it has a gradient term. And you could have, again, higher order terms. All have to respect the two basic symmetries that we have. One is invariance in spin space. In the Ising model, it was an up-down symmetry. Now we have rotational invariance in the space of phi. So as you rotate phi, you have to recover the same object, and that's why you have scalars here, phi to the power 2, phi to the power 2, and then squared. Those are scalar quantities. They are invariant under rotations, so in general SON, if you like. What I also need to respect is rotational invariance in space. And therefore, when we look at the gradient term, I simply write it as gradient phi. What I really mean is written out here in explicit detail. So what I mean is a sum over all space. So I is the index going from 1 to d. So let's say 2 or 3 or 4 dimensions. And the index alpha that we have here runs from 1 through n. That's, as I said, the index that's for the vector field. 1 Ising, 2 xy, and 3 the Heisenberg model. And you see the construction is such that I contract the indices I for space, and I contract the indices alpha for the vector components of the spin. And that means I have rotational invariance in space. That's why I'm contracting the indices I in space. And I have rotational invariance in the spin space, or in the vector space of my vector field theory. Okay, that's why you have this particular construction, because it obeys all the essential symmetries. And that's really a big advantage of starting from these kind of Ginzburg-Landau models. Because if you would invest the time of deriving it, you would just waste your time. Okay? You would waste your time because from all that you have here for the critical phenomena that we study, the coefficients, the value of R, the value of C, and the value of U don't matter at all. They're totally unimportant. That's not the essence. So investing time in calculating those parameters is an interesting endeavor. But for the critical phenomena, you don't need them. And that's one of the biggest insights that you have when you study those Ginzburg-Landau functionals, that you can start from a heuristic picture alone without deriving those things bottom up. You can right away start with such a phenomenological model. Now, when you have such a generalization of to an n-vector model, your propagator, so the correlation function between the fields, also changes. This is the correlation function in mean field theory, so it's our basic element that we use when we study the perturbation theory of these objects. And it's as before, so you have a theta function combination here that confines the momenta to this thin layer between lambda over b and lambda. That's our momentum shell. Then you do have the classical structure, 1 over the harmonic term. So you have just this term that you have here. You write it in Fourier space, and you get 1 over r plus cq squared. The other terms that come is a delta function. So this 2 pi to the power d delta function just means that those correlation functions, they are non-vanishing only if the momenta are equal and opposite. And then that's the new element that we have here, that this structure, the field theory that we have here, is diagonal in the indices for the vector components, and therefore we have here a delta alpha beta. That doesn't have to be the case. If there's some reason why there's an anisotropy in the system, you wouldn't have that. But here, because we assume a n-vector model with such a rotational symmetry, that's the structure that you have for the propagator. So far, so clear? Speed is okay? Okay, good. But please interrupt me anytime. And now the second element, in addition to the propagator, is the perturbation that we have here. So this is our parameter or operator in which we want to expand. And we call this in general the vertex or a vertex that characterizes our theory. And you had seen this before. The vertex for the Ising model was just this cross with the 4 legs. And now I have to be a little more careful. If you look at the structure here, this is really, when you write it out, 1, 2, 3, 4 are the vector values of the momenta. So it's Q1, Q2, Q3, and Q4. And then you see here the indices for the tensor components, alpha, alpha, beta, beta. That means I square phi and I square it again. And that's why I have the structure that I contract alpha with alpha and beta with beta. Okay? And therefore, if I want to have a proper representation of the vertex, I need to visually also express that fact. And I do this by combining on one side of the vertex those legs that have the same identical tensor index alpha. And I do so in the same way, having the same tensor index here on the right-hand side. And this dashed line here you can read as an indication of the U that you have here. So, yeah?
Can you please explain again where the momentum shell comes from?
Because we do Wilson momentum shell, so our perturbation theory is based on the fact that we integrate over the momentum shell. That's our choice in the Wilson calculation. If you were to set up a perturbation theory where you don't do the shell elimination of Wilson, but you do a perturbation theory for the full thing, you wouldn't have that. Then you would just have a theta function that confines you to be below lambda, because that's the cutoff of the theory. So the way we set up the perturbation theory is that we want this infinitesimal onion-like tracing over the degrees of freedom in the Wilson sense. That's why.
And what's the motivation for that?
The whole RG procedure, right? So the whole RG procedure was that we wanted to perform the trace not in one go, but successively to set up the RG flow. So it's the whole setup of the RG that rests on that fact. It's the same thing as what you do when you do a decimation procedure in Karanov's case, where you say you want to have a free energy that remains the same, but you successively trace out the spins on a local scale. You renormalize, you trace out, you renormalize, etc. And the Wilson scheme with momenta is the same thing, just in momentum space and not in real space. Okay, so we want it successively. You'll see in a second, maybe in the second half, what would happen if I were to do the perturbation theory right away. Right? You could also say, let's just calculate the correlation function from the theory that we have and do a perturbation theory in the coupling constant. But that's a different approach, and you'll see how the two are connected maybe in the second half of today. Other questions? Okay, so that's the setup. That's the setup that you need for a momentum shell Wilson RG. Yeah, please.
So if you have the expectation value of phi alpha and phi beta, where do they bench, or why do you get this 1 over r plus c q squared term?
Because this is the propagator or the correlation function of the harmonic theory. That's the one we expand around. And the harmonic theory is just the two terms that you have here as the first two terms. And all you do is you write this in Fourier space, then the nabla becomes a q squared. And as you always have, if you calculate correlation functions, you get the inverse of what you have in the free energy. It's just by Gaussian integrals, if you integrate over something harmonic, you get it downstairs in the denominator, and that's what you have here. So it's just a Gaussian correlation function of this thing. Okay, that's our setup for the perturbation theory. And it's not really more complicated than the perturbation theory we already performed for the Ising model. The only complication that comes in is because of these indices alpha and beta. So the tensor structure changes, but not the counting in terms of the momenta that you have. So the integrals stay the same. And as you will see in a second, all that changes is the combinatorics. So let me go. So here I emphasized it, but let me go through. So we want a momentum shell approach. So over this red area, we integrate over. That's the idea. We do perturbation theory successively by integrating over these modes and leaving the blue ones alone. They're kept as is. So therefore, if we look at the vertex, we need to dissect the vertex into that part that's in the blue region and the part that's in the red region. So I write this as phi q lesser, that's inside, plus phi q larger, that's the red shell that you have. You square it again, and as you multiply this out, just by very simple binomial formula, you get this vertex to be one which has these terms, where the black lines, as usual, are those inside. The red lines are those on the shell, and by, as I said, using binomial formula, you get one term here, two of those kind, where you have two red lines on one side, four of those, and you can do the counting, right? So you get two either by using binomial's formula, or you can just ask how many ways are there I can put the red lines here, and there's two. I could put them on the right, and I can put them on the left. You can ask how many ways can I put the red lines here? Well, I can put one red line here or there. That's already or there. That's four cases. Right? So I have four cases, and the other one is then fixed. And that has no choices that you have. So instead of counting binomials, which is just multiplying things out, you can for yourself make yourself a rule set that translates the diagram into a multiplicity. It's very elementary. There's no magic with that. It's just counting. Now, let me write down the diagrams. And again, stop me anytime. The diagrams then for the average are those two. And they come from the fact that I can close the internal lines either on one side of that vertex, or I can close it by connecting the two sides of that vertex. Yeah?
Why wouldn't we have three red legs and one leg?
Well, you can do the count. Okay. Yeah, you can have them, but they would not contribute to this object that we have here. We had it before, so when you remember what I did just a few lectures before, when I wrote down all the different diagrams, I had cases like so, and they would contribute to other types of vertices. So here I choose those which are those that will contribute to the renormalization of the mass and the renormalization of the phi to the fourth term. So good point. Thanks for noting this. I selected those. Okay, and if you have those diagrams here and you have just one leg, you can't close it. It's zero by symmetry because you integrate over Gaussian, and if you have just one, a single value, you can have phi to minus phi symmetry, and then this one doesn't contribute. Yeah.
Sorry, once again, what do the red lines represent?
Those on the momentum shell. So I tried to have the same color. So the color red here is the color red there. So it's those fields that carry momenta that are on the shell. And I want those to be integrated out. Those are to be eliminated. And the blue ones, alias the black ones, are to be kept. Right? This is this basic idea of RG. You successively eliminate modes, those are the red ones, and you keep the black ones. And you do it again and again and again to get a flow in the coupling constant. And then you want to see how is this flow in the coupling constant behaving. Other questions? Yeah?
So the blue dashed line is not, does not represent
the dashed line is just an artistic way of getting the alphas apart. So I know that the indices, so the dashed line makes me remember that those have the same indices alpha and those have the same indices beta.
But the black lines are the one that the ones that are in the blue region, basically.
Yeah, sorry for the color mismatch. The blue is just meant to be connecting the two parts of the vertex. So the black is the blue. Yeah.
Why are we looking only on the U term and not also on the C term and R term?
Say it again.
Why are we looking only on the U term, like the phi squared, squared, and not on the like R and C term, like the phi squared and nabla phi squared?
Because we can deal with them exactly, right? So the trick of a perturbation theory is the theory can do exactly, which is a Gaussian theory, you take as your base, because you can do Gaussian integrals. So the very basis of us being able to write this down is because we can perform the Gaussian integral and calculate that correlation function for a Gaussian. And that's the reference point around which we expand. And this one we can't deal with. That's a nonlinearity. We cannot do the path integral with a nonlinearity. We can just do it for a Gaussian. And therefore, we keep the Gaussian where we can do all the integrals and expand in the object we cannot do exact calculation in. Okay. So let me go through. So here, when you have those two diagrams, there's a basic difference between this one and that one. Why? Well, here I said I'm having alpha, and I'm contracting it. So I'm having a correlation function phi alpha, or phi beta, as I have it here. And I have to perform the sum over beta. Now remember, the propagator are delta, alpha, beta. So all these terms are the same. And as I perform a sum of n terms that are all identical, this one will give a factor of n. Right? So the multiplicity of this diagram is n and not 1. And here it's different. Here I'm connecting an index alpha with an index beta, as you see here, alpha, beta. And as I have a delta function, I don't have what I have here, the sum over beta separately. So this only counts 1 and not n. And in addition to this factor of n and the factor of 1 that you have here, you have the multiplicities. So when we go back, we had here this factor of 2 from multiplying out the terms. Here we had a factor of 4 of multiplying out the terms. And when you go here, those are the 2 and the 4. Okay, and now you combine things, and then you get n plus 2 times u, the n coming from this one, and the 2 coming from here, because here you have 4 and 2, so it's a difference by a factor of 2. And now you can make a check, because we have done the calculation for n equal 1, right? And remember, there we found 3. So it's all fine. It reduces to the Ising case that we have. And I emphasize again, the only difference really is that because of this tensor structure, the counting here is different, and I have this factor of n because I close the loop over n different legs that we have. Yeah?
Why do you only consider these two configurations here and not the one without any red lines or with all red lines?
So I want an object, so there's more. So this average here has more terms. It has also one where we only have external black lines. And that's the R. That's the original one that I keep. This is this term here. Right? I don't write it down. I just have that to begin with. And those are the additional contributions that are new. They change the R that I had previously, right? And it changes it because those are terms that have two external fields. So this contribution is phi alpha smaller, phi beta smaller. So they have the same form as my original term, which was R phi squared. Okay? So they add on to what I had already, and there would be terms where you have just red lines outside. They are constants. They don't change the R. They change the free energy. They shift the free energy, but they don't shift the mass term. So I select from this whole thing those contributions that are changing my mass term, the R term that I originally had. So you should not read this literally. It's not an equal sign. It's an equal sign conditioned on me selecting those contributions that are relevant for the question of how the mass is renormalizing. Clear? Okay. Okay, so that's what you find. And now fun starts when you have more than just a single vertex. You go to second order imperturbation theory, and you can impress your friends by drawing these kind of diagrams. I don't know whether they're impressed by that or not at all. I wouldn't. It's just a bookkeeping device. I think, some people have this mystical view of Feynman diagrams as being something super cool, but they are not really super cool. They're just a very, very basic bookkeeping device, right? And it's a neat way of avoiding writing a lot of stuff and getting a problem with your arm, right? So you just draw little nice pictures. And they are useful because they really summarize the complicated algebra that you would have to perform otherwise in a very simple form. And this simple form here is expressed in these numbers that I write down. So the 2 times 2, those are the two binomial factors that I had. Remember, I multiplied out the diagrams. I had 2 times those type of diagrams and 4 times those where the red lines are on 2 different vertices. Those are the 2 by 2. Okay, and then here I'm contracting internal lines, and I cannot do it for you, but you can do it this way, up, this way, down, or you can swap your fingers. Right? There's 2 ways of connecting the internal lines. Either you connect this and that, or this with the lower one and that with the lower one. Those are the 2. And once you connected them, they are summing over the same index, because they're on the same side of the vertex. So you have a sum over alpha, and that's n. So you have 2 times n, done. Okay, that's the multiplicity of that diagram. Here, a similar thing, the 4 by 4 is just from expanding out the vertex, from getting those binomial coefficients, or by saying how many ways are there for me placing all the external legs that I have that I don't integrate out. And that's 4 choices times 4 choices that I have. And then internally, once you have chosen the external legs, you have to connect these red lines. And again, you can connect this one with that one and this with that, or you could connect it down and this one up. But that would be the same thing. So this is the factor of 2. Those are the external legs times the internal connections. Same here, multiplicity of choosing the external legs times the multiplicity of doing the internal connections between the red lines. Yeah.
So on the last slide, with the first order terms,
Yeah.
why does so if we integrate over the phi's for the phi larger,
Yeah.
we get these closed red loops.
Yeah.
But we also integrate over the phi smaller, so why don't we get closed black loops?
Because we keep them, right? So I can't write on the board, so I have to say it in words. So we have the free energy, and we have then on the right-hand side a partial trace over those modes that we integrate out, and before that we have the total trace. The total trace of those in the blue region. And this one we don't touch, so we leave it. So we do this, iteratively. It's this divide and conquer approach. You do a little thing first, but you keep the outer part untouched. So they are integrated over. You're right. There's an integration, but they're not averaging. I leave them as they are. Just don't touch them. Yeah.
Why is it n for the internal term?
Because you have, well, here you connect different alphas. You take alpha and beta. Right? So you have a delta function that gives you a 1. If you have delta alpha alpha and you sum over alpha, you get n. The trace of a diagonal matrix is n. And if you pick one of the diagonal matrix, it's 1. Right? This is why I'd separated the whole trick of drawing the diagrams like so is that here I have the same index, the same tensor index. And if I'm here, I have the same index as well, but that index and that index, they're not the same. They can be different. And therefore, when you do the sum, you get, for those where you're connecting the same, you get a factor of n, and for those where you're connecting different sides, you get a 1. Okay? Just write it out for you. I mean, if you don't see it here, if you write it down, you'll see. And that means now our u prime is really the same as before. It hadn't really changed. All that changes is that I have to add up those different multiplicities. The integral is untouched. It's the same integral. It's the same c integral that we had before. You just have, instead of 9 that we had there, n plus 8, the n coming from here, the 8 coming from the rest. Good. Now you have that, and now let me kind of recapitulate for you how this diagram analysis or the Feynman rules or how you do perturbation theory in general works. It works here by drawing these diagrams, and in the case that we had it, we draw the diagrams with 4 external legs, which are not integrated out. Those are the black lines. Because I want, again to your question, I want those that are renormalizing the phi to the 4th term. So I pick specifically those that have the same structure as the original phi to the 4th term. That's why I pick 4 external legs. And they are untouched because I have the sum over those fields, but I don't want to touch them. I want to only eliminate the modes that are on the shell. So those 4 are the ones I want to keep, and the red ones I want to integrate out. And then when you do the integral, you have to assign momenta. And we know how to do this. The phi to the 4th term is a term that's local in space, and if you write it in Fourier space by Parseval's theorem, the momenta that you assign to the 1st, 2nd, 3rd, and 4th field, they must sum to 0 because you have a local term. You also have a delta function because the propagator that you use here, so if you connect this line with that line and draw a red connection, the propagator, because of the symmetry of your field theory, has a delta P plus Q. So you also have a momentum conservation along such a propagator. Yeah?
So the first order terms give us a correction for R because they are also quadratic in phi smaller, and the second order terms give us a correction for the U term because they're also quartic in.
Yeah, in the calculation we do, yes, but we could have drawn diagrams where you have one black line coming in here, another black line coming in there, and then internally have 3 lines connecting. I can't draw, sorry. And that would be second order. So there are second order terms that renormalize the mass. I've drawn them. You have them in your notes. They are there, but in the order we are interested in here, because we only want to go to the lowest order in perturbation theory, otherwise, it would take a long time to do all these calculations. It's as you say, okay? But not in general. All right, so we use momentum conservation at the vertices and the structure of the propagator. So delta alpha beta is one of those structures of the propagator, and delta P plus Q prime. Then that's what you use, and then you do the multiplicity. So this was this counting rule with the number of choices you have for the external legs and the number of choices that you have for connecting the internal ones. The external legs is multiplying out a square, so it's binomial coefficients. The internal legs is using Wick's theorem, so it's also counting the number of terms I can connect terms in a average. And then the rest is you perform the integral. And this momentum shell integral, as you saw, is super trivial because you don't really have to integrate, as you saw. The momentum shell is tiny, so everything is just the value of the integrand times the thickness of the shell. Okay? So it's not rocket science, it's just very elementary bookkeeping and very elementary integrals where you don't even have to integrate. Good, and then the upshot of the analysis is that you get a flowing set of coupling constants. You get a flowing value for the mass, for the term that is in front of the phi squared, and you get a flowing coupling constant U. And the flow of these two terms, so of the mass and the coupling constant, is given by the right-hand side. And you should notice that in this right-hand side, not a lot of stuff comes in. So what comes in is basically the structure of the field theory, which is encoded in the constants that you have. And then you should notice, because we generalized to n components, what really comes in importantly is how many components you have for your field theory. That's key. Changes the flow equations. And then you can check what kind of behavior is there of these flow equations. Is there a fixed point? And here we can declare victory because there is a fixed point. And this fixed point is one that's of order epsilon in the coupling constant phi to the fourth. And there's also a fixed point in R that you have by looking at the RG equations. And that means that this general scheme that I tried to explain to you with renormalizing Hamiltonians is really working out here. You do have a fixed point. And because you have a fixed point, just by the very fact that you have a fixed point, all the other things follow immediately. Okay? So the existence of fixed points is really the key. And then, as you also learned from the general scheme of a momentum shell integration procedure, the linearized flow in the vicinity of that fixed point, the eigenvalues that you get by linearizing the flow, those eigenvalues, they are the core quantities you need to calculate the exponents. Once you know the eigenvalues, you know the exponents immediately. So that's what we do here. You look at the flow, you've seen that before, and then you linearize. And let me recap, because I think it's really key that you understand this, even if I'm saying this twice. So you expand around the fixed point and take small deviations, delta r and delta u, around the fixed point that we have. The fixed point itself is stable below 4 dimension, the Wilson-Fisher fixed point, and above you switch the stability, as I explained to you. Then as you look at the flow equations, you get this kind of structure for the flow equations. You look at this in matrix form, and I guess you all know how to diagonalize 2 by 2 matrices and get the eigenvalues. That's really trivial, because especially here, this is an upper trigonal matrix, which the eigenvalues, where the eigenvalues are simply the diagonal terms that you have. So the diagonal terms are the eigenvalues. Lambda tau is this one, and lambda u is minus epsilon, just reaffirming what I said. If you're below 4 dimension, the Wilson-Fisher fixed point is stable, and the Gaussian fixed point is unstable, and above 4 dimension, it's just the other way around. The Wilson-Fisher is unstable, but the Gaussian fixed point is stable. Now, once you have the exponent, you just go back to your lookup table, which is really independent of the particular scheme that we use. And then you find nu is 1 over the exponent that we have for the flow of our relevant field that corresponds to the temperature. I expand this back up again, because strictly I have to do it in order epsilon. So I don't just write 1 over lambda, but I up expand lambda t such that it's all in the numerator, right? So I get then a half plus this value, and you see it's a half to a leading order in epsilon. That's the mean field exponent. That's the one we got just by ignoring the 5 to the 4th term completely. But this value is changed. The exponent of nu is larger than a half, and it's larger by this amount. And now you see something which I emphasized already, but here you see it very, very clearly. Question to you: what enters the exponent? Only n. Only the number of fields that you have and the dimension of space. Nothing about the value of r, nothing about the value of u, nothing about the value of c. So these microscopic values are just totally unimportant. They don't matter at all. And this is the beauty of renormalization group theory and critical phenomena, that the calculations that you do and what you find here as a main result is universality. Whatever these theories are and whatever effort you put in calculating them, it's obsolete once you have the structure of the theory. All that's really determining the value of the exponents is the number of components and the dimension of space, nothing more. And that's a very deep insight into the behavior close to a critical point. Because that's not obvious to start with, right? Who would have guessed that once you're at a critical point, all these microscopic details are irrelevant? And here the RG is the proof of that that's the case. Now for alpha, this goes on. For alpha, we find this. It's 2 minus d nu, 4 minus n, divided by 2 times n plus 8. Same thing, dimension enters and the number of components. Same for beta, same for gamma. And now a big question, of course, how good are those values? They are so-so, right? They are not really perfect in comparison with Monte Carlo simulations where you can determine these exponents exactly, but they go the right direction, right? They go the right way away from the mean field value. Yeah?
What happens if you go to higher orders? Because
yeah, good question.
typically 1 or something like this.
No, it's a very good question. You can go to higher order, and people have done that. It depends on how how diligent you are or how brave you are to go to higher order. So if you're interested in values of exponents, if that's your interest, then you should go to higher order. And you can reasonably go to second order with some effort that you can do. The Ising model has been studied to, I don't know, 6th or 7th order by people in Berlin, so around Kleinert. And once you have such a high order in perturbation theory, which you can achieve, then you can resum the series that you have by approximation schemes that are called Padé approximations. And once you do that, you actually get pretty accurate values for the corresponding exponents. Having said this, it's more important to do the first order calculation because that informs you about where things go, what's relevant, what's irrelevant, in which directions do the exponents go. That's the key information. The values of the exponents is more or less, you know, how sporty you are in doing diagrams. And the easier way, and the insight is not larger by doing higher order loop calculations as compared to doing Monte Carlo simulations. That's the same kind of insight. It's just whether you like calculations more with your pencil than with a computer. I think that the point in RG calculations is not so much the value of the exponents, but the fact which terms in the Hamiltonian matter and which terms don't matter. So what are the key insights from the renormalization group analysis that we have? So take a bird's eye picture, leaning back, what have we achieved by doing so? And in saying all this, this is not just something which people know for the Ising model. It's true for many other models as well, and it's kind of a framework of thinking about systems that are many-body systems in general, right? Because if you think about a many-body system, then you could have 2 points of view. You could try to get all the details right, or you say, I don't care about the details, and I just want the overall behavior. And what RG tells you is that if you don't care about the details, you're actually right. And if you would care about the details, you can also be right, but it doesn't help you. There's a famous saying by Keynes, which I agree to, saying it's better to be roughly right than precisely wrong. So here we go. What you have here in the G language is you have a controlled expansion that allows you the scaling laws close to a critical point and understand why there is universality. And this is the picture that you always should have in mind. You have a space of coupling constants. In this space of coupling constants, there is a physical line that describes your set of Hamiltonians that you derive from microscopics or you guess by writing them down. And that space of Hamiltonians has a critical point which you know is a phase transition. So you know an Ising model has a phase transition from a ferromagnet to a paramagnet, and so has the Heisenberg model. And now in this larger space of coupling parameters, which are not the ones that the system actually takes on, it's a larger space that helps you think about it, you can define a flow, kind of a flow you imagine as you zoom out the system. So you go from small scales to larger and larger scales. So coming back to your question, I do this momentum shell integration because I do want to make the zoom out. Or I do make the decimation approach because I want to zoom out and I want to learn about that flow. That's our goal. And now you have that flow, and that flow is then very particular. This flow has a manifold, a critical manifold, where everything that is on that critical manifold flows to the critical fixed point. Meaning, so all directions that you have on this critical manifold, they are irrelevant because they carry you towards that point independent of where you start. So all physical systems that are on that manifold, not just this line that I drew here, but any other line that you can make will flow there. The difference may be how far you are from this fixed point. Because the further you are away from that fixed point, the longer it takes you by coarse graining to reach it. So the crossover from mean field behavior to critical behavior may depend on that. But once you're close enough to the fixed point, these crossover phenomena become narrower in scope. So there's this critical manifold, and on that critical manifold, because it's hooked to the critical point, and because this is a RG transformation, the correlation length is infinite everywhere on that manifold. Orthogonal, quote, quote, not really orthogonal, but in another direction, which is not on that manifold, these are all the relevant directions. And they carry you away from the critical point. And one obvious relevant direction is temperature. If with the temperature you're below Tc, you go to the low temperature fixed point. If you're above Tc, you go to the high temperature fixed point. So the flow goes either this way up or this way down. And then, as we saw, if you're close to the fixed point, you have a linearized flow. So relevance and irrelevance of operators is defined by this picture. You can estimate of the critical exponents by looking at the linearized flow. And as I emphasized before I started, this is actually a way of thinking. It's not just a set of tools, it's really a way of thinking about many body systems that as you look at larger and larger scales, there's universality and not something that depends on all the microscopic details. That's the very heart of statistical physics, right? If you think about the ideal gas law, which is really a classic and paradigm, the ideal gas law doesn't care about the nature of your particles, whether it's helium or other kind of gases. It's the same law for different kinds of molecules. So there's obvious universality in the ideal gas law. And here, this was really one of the biggest insights in the last century in statistical physics, that you do have this universality close to critical points. You have a question?
Yes, aren't we constrained to be on the physical line? So how can the flow carry us away from the physical line towards?
Okay, very good question. The flow is not a physical thing, right? If you are on that line, that's your Hamiltonian, that's what you have. You don't change that. That's nailed in stone. What you do is, by the flow, is you look at the system at a larger and larger and larger scale. You kind of squint your eyes. And then, in a way, if you would like a Hamiltonian, which is not valid on a, say, micrometer scale, but if you would like a Hamiltonian that's valid on a millimeter scale, then these flows actually have reality, because it's the behavior of the system is described by those parameters on the length scale that you are carried to by the RG flow. Yeah. Great, so let's stop here and have a break for 15 minutes, come back at 20 past the hour.